How does wave-particle duality work if not simultaneously observable? Imagine watching a magician perform a trick where sometimes you see a ball and other times you see a wave. The same object can appear as both, but never at the same moment. That's the mystery of wave-particle duality. In the world of quantum mechanics, tiny particles like electrons and photons can act like waves or particles, but not both at once. The trick is in how we look at them. When we set up an experiment to find a particle, like catching an electron hitting a screen at a specific point, it behaves like a tiny ball. It shows up as a single, localized spot. But if we change the experiment to look for wave-like behavior, such as interference patterns created when waves overlap, the same electron acts like a wave spreading out and creating those patterns. This is because the quantum object does not have a fixed nature. Instead, it has a potential to be either a wave or a particle. The principle of complementarity explains this. It says that wave and particle aspects are two sides of the same coin, but you can only observe one side at a time. The wave function is a mathematical tool that describes the probabilities of where a particle might be found. When we measure, the wave function collapses, and the particle appears in a specific spot. For example, in the famous double-slit experiment, electrons fired one at a time through two slits create an interference pattern over time, showing wave behavior. But each electron is detected as a single dot, showing particle behavior. If we place detectors to see which slit the electron passes through, the interference pattern disappears, and the electron acts like a particle passing through one slit or the other. This shows that how we measure influences what we see. The context of the experiment determines whether we observe wave or particle properties, but never both at the same time. This duality is essential in quantum technology. Devices like quantum computers and quantum sensors use this property to perform tasks that are impossible with classical systems. They relying on quantum superpositions and entanglement, which are rooted in wave-particle duality. In simple terms, quantum objects are like versatile actors that can perform different roles depending on how we choose to observe them. They have an inherent potential to behave as waves or particles, but the act of measurement decides which role they play. This fundamental aspect of quantum mechanics makes the tiny world both fascinating and powerful for future technologies.